Okay, so welcome back. This is Chapter 7 on water and atmospheric moisture, Introduction to Physical Geography here at Cal State Northridge. As usual, I present the learning objectives for the chapter here early on, and you can take a look at these. We're going to, in this first segment, take a look at the properties of water, talk about humidity. You should be able to explain the dew point. And then later we'll talk about atmospheric stability, and then hopefully you'll understand how parcels of air change according to atmospheric conditions, and then identify some clouds and the way they get formed. So let's talk a little bit about water first. It's colorless, odorless, and mostly tasteless if it's pure. And that's what you're thinking. Hold on, water has a taste, but it's the things that are in water that give it a flavor. Pure hydrogen and oxygen combined together as H2O is colorless and tasteless. And it's almost impossible to find pure water simply because it's such an amazing solvent. It'll erode just about anything, and bits and pieces molecules of other things are swept up within the water, and that's what gives water its flavor. Water in its purest form is the basis upon which a lot of scientific measurements get made, because it's the most abundant thing basically on Earth. 1 gram of it is 1 cubic centimeter, and that's where a gram comes from. That's how we know what a gram is, and that's essentially where a centimeter comes from as well. Our body is made up of 70% of water, and without it we can only survive a couple of days. Most of the earth is covered by water, 71% of the earth's surface, and that's not really considering the depth of the oceans as well. Where did all the water come from? It appears to have come from comets and other debris that crashed into the earth that had a great deal of hydrogen and oxygen. Water can emerge from deep within the earth's surface through a process called outgassing, and a good bit of essentially water vapor gets into the atmosphere through eruptions of various sorts. Water has some very peculiar qualities, and I urge you to read the chapter slowly on this point, because I'll probably ask you a couple of questions. It's more in the physics realm, but it has a lot to do with a number of the earth processes that we will look at later in the semester. When water cools, the molecules move around a lot less, and so water becomes more dense as the molecules require less space between themselves. But it reaches a maximum density at 4 degrees Celsius, just above freezing. Below that, water begins to freeze, and it expands during the formation of ice, and it increases in volume. So that means it gets bigger. And anybody who's left a can of soda, which is mostly water, or a bottle of something in a freezer will understand this the hard way. I've unfortunately left cans of soda in an automobile in Ohio or Chicago on a freezing night and come to open the car to find it had exploded. There's just the formula for density. So there's a 9% increase in volume and a 9% decrease in density. But pure ice is less dense than water. And so that's why ice floats in a glass, and that's why icebergs float on the ocean. It's one of the very few liquids that float in its liquid form. And you can consider how peculiar the world would be if all of the icebergs or all of the ice in the world floating in the oceans were to sink to the bottom of the ocean. It would have massive repercussions for life on Earth, and we may not be able to, the Earth would perhaps not be as habitable as a location for us. This expansion of water in the formation of ice has enormous consequences for a number of things. Engineers that build roads, and certainly you that have driven on a road that has been subject to a lot of freeze and thaw cycles, know that there'll be a lot of potholes. It breaks roads. If you've ever lived up north where it gets really cold, you have to worry about your pipes freezing and busting in the winter. It can damage the engine. It can sink ships. But it also is an important factor in the erosion, the damage, the breaking apart of rocks, of entire mountains into boulders and smaller rocks. So water comes in three states: gas, liquid, and solid. And so let's start with liquid, since this is the phase that we understand most. And in this phase, the molecules of water, the H2O, is bonded loosely. So I like to think of it as Legos that aren't fully stacked. And as the water gets colder and it loses energy, it turns into ice at around 32 degrees Fahrenheit or 0 degrees centigrade. And at that point, water molecules begin to attach to each other in a crystalline structure that's always six-sided. And it's sort of like those Legos being stacked in a fashion where all of the little feet are connected into all the little holes in the Legos, and they can't move. If, on the other hand, molecules of water are heated up, more energy is applied, and they absorb more energy, they begin to move about so much that even the little bits or parts of the water molecules that are attached to each other can no longer stay attached, and they break apart, and that energy allows them to spread apart. And when they spread, they become more voluminous, they spread out, and their density becomes far less than the atmosphere that surrounds it in general, and it causes it, for the most part, to rise. And again, this is all you have to keep in mind, that this is a matter of energy. When energy from the water at a gaseous state decreases, then it will retreat back to liquid water, and that process is called condensation. There are 6 vocabulary words here that you need to know: condensation, vaporization, freezing, and melting, which you probably already know. But the more challenging ones, or the new ones to you, may be sublimation, which happens when ice turns straight to water vapor, and that will happen on a snowy day when the conditions are right, where snow and ice will go straight to gas. And then when gas becomes cold very rapidly, it can do something called deposition, which is when frost forms, where water vapor touches something that is quite cold, like your car or a blade of grass or the roof of your house on a very cold day, and it converts itself from gas. It loses energy so rapidly that it more or less skips the liquid stage and goes straight into the crystalline state, which is ice. Pay special attention to this diagram from your book. What I think is important for you to pay attention to is that this measure of energy, calories, is a perfect 100 calories to take 1 gram of water, that's 1 cubic centimeter of water, and heat it from a frozen state all the way to its boiling point. That's 100 calories. When water that is 100 degrees at its boiling point cools all the way down to its phase change to ice, or a crystalline structure, that's 100 calories that is released into the atmosphere. To get water from 100 degrees to vaporize, it's 540 calories, and then for it to go from 0 degrees all the way through the phase change to ice, it has to lose 80 calories of heat into the atmosphere. So keep all of this in mind, because it helps you understand what's going on out in the atmosphere. This term latent heat has been popping up repeatedly throughout the book, so it shouldn't be too much of a surprise to you. The last of images for this segment here is this graphic designed to show you how this caloric release of heat works in the atmosphere. So if there's a rain cloud going by and the water vapor in the air condenses to clouds and then later condenses into water droplets far enough to fall onto the ground, perhaps at a nice 68 degrees, that is a release of 585 calories of heat energy back into the atmosphere. Now, when that heat passes back over, say, a lake or these trees, and there is water, liquid water, that water will absorb 585 calories in order to get it back up into the atmosphere. That's per gram of water. So if you think about how many grams of water fall out of a cloud during a rainstorm, then you get an idea of the immense number of calories that are being released as heat into the atmosphere during a rainstorm, or alternatively, how many calories of energy is needed to heat water enough to get it to evaporate